Hello everyone, welcome back to the video. So today we're going over heating and cooling curves. Specifically, how do we interpret the data presented on a heating and cooling curve? You do now, we're just going to do this heat equation, and your homework is the review sheet. But before we do this heat equation, I want you to take a look at this nifty guide that I made for you. So, have you ever looked at a heat equation and went, I have no idea what to do? Now, you will have an idea what to do, because this is showing you all of the heat equations and what to look for. So for your heat of your specific heat capacity, the Q equals mc delta T, you're looking for a temperature change. So for example, the problem's going to say from 40 degrees Celsius to 100 degrees Celsius. Notice the temperature is changing from 40 to 100. So because of this temperature change, we're using this formula, which is located on table T of the reference table, as in terrific. I do not need to remember this. And you have your C constant, which is 4.18 joules per gram degree Celsius, and that is located on table B, as in believe it, I don't need to remember this. And again, your heat of fusion, that's the Q equals MHF. You're looking for keywords this time, those keywords being freeze or melt. If it's not one of these two words, it is not acceptable. And I don't want to see the word melting point, or freezing point, because those are not the same thing as the word melt and freeze. When you see those keywords, you're going to be multiplying the mass by the heat of fusion, which is 334 joules per gram. You can find this formula in table T, as in terrific, I don't need to remember this. And you can find the heat of fusion formula constant on table B, as in believe the fact that I don't need to remember this. And finally, you have your heat of vaporization. Q is equal to mHV. Your keywords for this are boil, evaporate, or vaporize. You can find this formula on table T, as in terrific, I don't need to remember this. And you can find the constant 2,260 joules per gram on table B, as in believe that I do not need to remember this. So let's go through that do now that we know. So how much energy is required to boil 37 grams of water? Now your key word here is boil, which means we're going to be doing our heat. We're going to do our heat of vaporization. So again, the formula is Q is equal to mHV. So we know our mass is 37 grams, and we know that our HV value is 2,260 joules per gram. And when working on this formula, we can eliminate our grams, because we know that we have 2 grams. So we're left with joules as our final answer. So now we're just going to multiply that real quick. That is 37 times 2,260, and you get 83,620 joules. That's your answer. Okay, so let's get into today's topic. Hold on one second. So anything that I star or underline, I would recommend that you copy down in your notes. So what exactly is a heating and cooling curve? A heating and cooling curve basically looks at the relationship between kinetic energy and potential energy. Now, what's kinetic energy? Kinetic energy is the energy of motion. Remember, I'm walking down the street. I'm using my kinetic energy. Stop. Potential energy. So, again, the only way you're going to be able to walk down the street is if you're using motion. So again, kinetic energy is the energy of motion. Meanwhile, your potential energy is your stored energy. So again, all I really want you to copy down from this is that temperature is a direct measure of the average kinetic energy. So, with that said, as the temperature increases, your kinetic energy increases. As the temperature decreases, your kinetic energy decreases. As the temperature remains the same, your kinetic energy also remains the same. The way I like to think about this is think about if you're walking on, or better yet, think about it like a hot potato. If I came up to you and said, here you go, hold this really hot potato, what are you going to do? Are you just going to hold the potato in your hands till you get third-degree burn? Or are you going to kind of like rock it in your hands because you don't want to burn your hand entirely, so you're just going to move it around a lot? You're going to move it around a lot. So, again, when the temperature is hotter, the motion is increasing. So when your temperature is higher, your motion of your particles, just like how you're holding that potato, are moving faster. There's more motion. So as our temperature increases, our motion increases, therefore our kinetic energy also increases. Note that during phase changes, your kinetic energy remains the same. So what's a phase change? Your phase change is basically when your states of matter go from one to another. So for example, solid to liquid, that's melting. Liquid to gas, condensation. Gas to liquid. Oh, wow. Hold on a second. I'm so sorry, guys. I was thinking ahead a little bit. Solid to liquid, melting. Liquid to gas, evaporation. I am so sorry. Then gas to liquid, that's condensation. And from liquid to solid, that is freezing. Anywho, there are also two other phase changes that we are going to talk about. So again, just take notes of anything that I'm starring or underlining. Potential energy, all I want you to write is that is the stored energy found within the substance. And that when kinetic energy changes, your potential energy remains the same. And vice versa. If your potential energy is changing, then your kinetic energy is going to remain the same. So on the next slide, I'm going to actually show you what a heating curve looks like. So basically what I'm really expecting. So this is what a heating curve looks like. What I expect for your notes, though, is the following. So you're going to draw a y-axis. You're going to draw an x-axis. You're going to label your y-axis as your temperature. You could also label it underneath in parentheses as kinetic energy, which Ke is kinetic energy. And the bottom is your potential energy. Pe is potential energy. The way that we draw this, we're going to draw up, straight, up, straight, up. And we're going to label our areas A, B, C, D, and E. Now what's happening in these areas? Good question. So again, by the way, I just want you to label this diagram as the heating curve. So just make sure that you label this diagram, make sure you write down everything I'm writing down, because the next slide is going to look at your relationships, like what's happening there and what's happening to the kinetic and the potential energy, which you need to know. Copy down the whole table. By the way, you're going to see RTS used a lot today, and that just means remains the same. So, for these images, point A is a solid. Point B is your change from solid to a liquid, that's melting. Point C is a liquid. Point D is boiling. And point E is a gas. So just go back for a second. I'm just going to label these real quick. Location A is a solid. Location B is our change from a solid to a liquid. Location C is a liquid. Location D is our change from a liquid to a gas. And location E is a gas. So you got to know the names of your phase changes. Solid to liquid is melting. Liquid to gas is boiling or evaporating. And also you got to know what's happening with the kinetic and potential energy. So if I go back, we see that in location A, our temperature is increasing. Because remember, when we're reading this, we're reading it like a book. So we're reading it this way. So when we're going up, what is happening to our kinetic energy? It's also increasing. When one thing changes, the other remains the same, so your potential energy remains the same. Now during your phase change from solid to liquid, location B, as you can see, the temperature is not changing. So because our temperature remains the same, that means our kinetic energy is also going to have to remain the same. Meanwhile, our potential energy, because one is not changing, the other one is going to change. So potential energy will increase in this case. And again, liquid is increasing in temperature. As you can see, it's going up. So that means that our kinetic energy is going to increase and our potential is going to remain the same. Liquid to gas, I'm going to go back and show you. Liquid to gas, the temperature is remaining the same. So because of that, our kinetic energy remains the same and our potential energy increases. Finally, our gas. As you can see, our gas's temperature is increasing. So because of that, our kinetic energy increases and our potential energy remains the same. So in terms of questions on the exam, how am I going to ask you about this? I am probably going to give you a line segment, and I'm going to say, okay, what's happening at this line segment? Like, what state of matter is there? What phase change is there? And you just tell me that. I could also ask you, okay, at this line segment, what is happening to the kinetic energy? You're going to tell me increase, decrease, or remain the same. Same thing with potential. So you might have noticed that your choices here are either increasing or remaining the same. So the way that I like to remember that with a heating curve, your choices are only increase or remains the same, is I like to think of the phrase heating up. So when you heat something, it's going up or remaining the same. Next slide. This is a cooling curve. So the way I expect you to draw it is the following. Again, you're going to draw a y-axis, going to draw an x-axis. On your y-axis, this is going to be your temperature. And you are going to have your kinetic energy here. And then down here, you're going to have your potential energy. And this diagram's a little bit different. So the way we draw it is we go down, straight, down, straight, down. And I'm going to make that corner just a little bit more defined. There we go. And again, we're going to label our segments. So I'm going to keep the labels similar to where they were before. A, B, C, D, E. And again, just so you know what's happening where, your A, I kept these the same for a reason. Your A is still a solid, your C is still a liquid, and your E is still a gas. The difference is your phase changes. At B, it's going from a liquid to a solid. At D, it's going from a gas to a liquid. So again, remember when you read this diagram, you are reading it like this. And again, just make sure you label this as a cooling curve. Okay. So again, you're just going to write everything I circled here. So again, in terms of our states of matter, we still have everything the same as before, except now B, going from a liquid to solid, which is freezing, and D, we're going from a gas to a liquid, which is condensation. So what's happening here? If we take a look at A, and again, we're reading like this, which means we're reading from here down. So notice how we're going down as a result. So that means that our temperature is decreasing, so our kinetic energy is also decreasing, which means our potential energy remains the same. During our phase change, we see the temperature is not changing, so that means your kinetic energy remains the same, and your potential energy, since it's going in a general downward spiral, kinetic energy is going to decrease. Liquid, as you can see the liquid, again, we're reading it like a book, so we see our liquid is going down. So because of that, since our temperature is decreasing, our kinetic energy is also going to decrease, and our potential energy is going to remain the same. During the condensation phase, we see that our temperature remains the same. So that means our kinetic energy will remain the same, and our potential energy will decrease. Because remember, we're reading this way. And finally, for our gas, we see the temperature is decreasing, so that means our kinetic energy decreases and our potential energy remains the same. So, again, the way I like to think of this one, because now it's either decreasing or remaining the same, I like to think of the phrase cooling down, something you do after a workout, a cool down. So when it's cool, you either decrease or remain the same. Finally, let's talk about some phase changes. So these are substances must either gain or lose energy as a result of the phase change to occur. So first of all, before we even get into that, let's go over exothermic versus endothermic. An exothermic reaction releases energy. So think of it like exhaling. So when we exhale, we are releasing air from our lungs. Meanwhile, so that would mean exhaling, releasing air. Exothermic, releasing energy. Meanwhile, endothermic absorbs energy. So, for our endothermic reactions, we have solid to liquid, which is melting, liquid to gas, boiling, and one of our new phase changes that you may have never heard of, called sublimation. Sublimation is the process of going from a solid to a gas. You do need to know this for your test, hint, hint. So, an example of sublimation, because some people might have a hard time visualizing a solid becoming a gas. The closest example I can think of is probably dry ice. So, you have the solid, and the moment it touches something a little bit warmer, all of a sudden, it turns to this bubbly, cold gas. So that is the process of sublimation. Meanwhile, an exothermic reaction, that's not what I meant to do. An exothermic reaction is going to be condensation, freezing, and depositioning, our other new player. So what is depositioning? Depositioning is the process of going from a gas to a solid. So when you see depositioning, you might have seen it before. Have you ever gone into your parents' car or your car, if you're learning how to drive, on a winter morning and notice these little tiny ice crystals on your window? That is depositioning occurring. What's happening is the air is so cold that the moment it touches your window, it instantly becomes a solid. So that is what depositioning is. You do need to know that for the test as well. Hint, hint. Easy way to help you remember that sublimation is going from a solid to liquid is notice how sublimation starts with the letter S. And it also starts with a solid, which starts with the letter S. Just in case any of you are having a hard time or mixing up the two. Just so you're aware. And one thing that's not going to be on your test, but I do want to kind of bring up. What is crystallization? Now, you don't need to know what crystallization is for the test, but I'm bringing it up because the process of crystallization actually looks like freezing. It's basically when you create a liquid that's so concentrated so that the moment you put something new in it, it's going to look like it's freezing. It's going to crystallize because that's the process of becoming a solid crystal. In actuality, this is not freezing. It looks like it's freezing, but it's not. You might actually notice that when you touch a container that's going through crystallization, it actually burns your hand because it's releasing heat. So again, crystallization is not freezing, just so you know. And so what I'd like you to do now is I'd like you to go to the exit ticket. And on the exit ticket today, it is asking you, what is happening to the potential energy and kinetic energy during the following phase changes, melting and condensation? So what I'm basically looking for, the format for your question is the kinetic energy is blank, but the potential energy is blank. And you're going to say that for both of these. And as always, thank you for listening. And I hope you all have a wonderful, wonderful day.